Alright, in this section here of Calculus 1, Applications of Differentiation, we're going to be working some optimization problems. So finally we're going to be able to put some of this derivatives and all that to some kind of use. And of course we're going to start out with something really simple. Alright, so here's the problem. Let me find a color here to write on. We'll use that color there. Okay, we want to find two positive numbers. So we are, make sure we've got everything set up here. We're going to find, and that's really too light. It's still kind of light. I don't know what's going on here. Try this. Well, anyway, we're going to find two positive numbers. Two positive numbers, and we're going to let these two numbers just be x and y. Okay, so we're going to let the two numbers be x and y. Alright, we darkened it up a little bit. Anyway, so we're finding two positive numbers. We're going to call the two positive numbers x and y, and we're going to say that the product is 16. So the product of the two positive numbers is 16. So x times y is equal to 16. So this is their product. And then we're going to say that their sum, x plus y, we want that to be a minimum. And of course, we'll write that just min in a different color. Alright, so what I'm going to do here is I want to get this equation here in terms of one variable, either x or y. So this is known as our primary equation, and this is known as our secondary equation. And in a finite course, if we were doing linear programming, we might consider this to be the objective function and these to be like a constraint. So what we're going to want to do is get this in terms of one variable. So let's say, for example, let's solve for x in this problem. So y is equal to 16 over x, right? Just bring the x diagonally down. And then what we're going to want to do is get this guy all in terms of one variable, and that's going to be in terms of x. So we're going to take this 16 over x, and we're going to substitute it right on in, right, for that y right there, since y is equal to 16 over x. And so now what I'm going to do is I'm going to rewrite this as s is equal to x plus 16 over x. So there we go, we got it all in terms of one variable. Now what we're going to want to do is take the derivative of this, but the first thing I'm going to do is rewrite this. So this is s is equal to x plus 16 times, taking this to the numerator, becomes x to the negative 1. Alright, then we take the derivative. So I'm going to say s prime is equal to, the derivative of x is 1, take this negative 1, bring it out front, times it by the 16x, subtracting 1 from the exponent, and we get x raised to the negative 2. Now what we're going to want to do is just go ahead, we say, okay, look, the derivative is 0, right? That's where we can find possibly a min or a max. And then we're going to have, and I'm going to go ahead and just put the x squared down into the denominator. And then what we want to do here is we want to solve for x in this problem. So I'm going to go ahead and say, okay, 16 over x squared is equal to 1. 16 is equal to x squared, bringing this up diagonally. And then of course we want to square root both sides. And remember, this is plus or minus, but we're looking for two positive numbers. Alright, two positive numbers. So it looks like x is going to be equal to 4, positive 4. So that's one of our numbers. And then to find what the other number is, we just simply come up here Alright, we found x, and now we want to find y. And I've got to go back down here. This video has been broken up into two pieces. Okay, so x is equal to 4. Alright, so we know what x is. So we take x, we plug it in. So we're going to have y is equal to 16 over 4. And of course y is also equal to 4. So we got our two positive numbers, and it turns out the two positive numbers are 4. Now the question is, is that really a minimum? We didn't do a graph or a line chart and test if it's a minimum, but it's pretty simple to find that. Now actually what I'm going to do, let's say that you know how to set it up but you forgot the calculus. Okay, you forgot how to do calculus, and working out there in the real world, I found a lot of engineers would do things like this that actually forgot the calculus. So, but that's okay, right? What we're going to do is we're going to go ahead and I just want to graph this. Let's graph this. Let's take a look at the graph, and we can determine from there where our minimum is going to occur. So let's go ahead and do that. We're going to graph x plus 16 over x. Alright, so this is the graph, and of course this is the area right here that we're concerned with. Okay. And right, so these increments here, this is 4, 8, 12, and you can see 16. So as you can see here, 4, okay, is occurring right here on the x-axis, and of course that's what we said that our x was going to be, was 4. And when we go straight up, you can clearly see in the graph right here that this is going to be a minimum. But remember what this graph is. This was the sum, remember, of the two positive numbers. So you could see that their sum actually is, it looks like the sum is actually going to be 8. Alright, 4, 8, 12, 16. Alright. So if we were to graph this, we would just look, okay, that looks like the minimum right there, and so we know what our x value is. X is 4. We would take it, plug it back into that secondary equation, right? So this was our secondary equation here to actually find what the y value is. So on all these optimization problems, what we're looking at is, looks like I scrolled a little bit too much. We want to have some constraints. I call these constraints the secondary equation, but we need to construct the primary equation, get it all in terms of one variable. At this point in Cal 1, that's what we want to do. Get it in terms of one variable, and that's usually solving for one of the variables over here and then plugging it in over here. And then once we do that, we just take the derivative, set it equal to 0, and solve for whatever that variable is that's in there. And that's basically what we're going to do with all of these optimization problems. So sometimes you're going to have to remember formulas to be able to construct this primary equation here, and you might need to even construct the secondary equations. And of course this particular one here only has one secondary equation. But that's basically it. So if you forgot your calculus, you can, as long as you can set these up and graph them, you can get a good approximation. All right. So I'm going to be working a ton of these things and some geometry problems, maybe some finance problems. I don't know, all kinds of problems. There'll be a bunch of them, probably about an hour's worth at least on here. So, all right. All right, working Cal 1 problems, applications of differentiation, they're optimization problems. And this particular one here, we want to find two positive numbers such that the product is a 25 and the sum of the first plus 3 times the second is a minimum. So we're going to set up our primary equation, our secondary equation, and then we're going to go through the proper steps to finding these two positive numbers. Okay, so I'm going to go ahead and write out two positive numbers. We're going to let x and y be our two positive numbers, And let's see, we're going to go ahead and write our primary equation. Now it was the sum of the first, I believe, I'm trying to remember here, it was the sum of the first plus 3 times the second. So 3 times the second. So this is our first and that's our second there. And so now we want to go ahead and write our constraint or our secondary equation. And we said that the product, I believe, was going to be 25. Alright, so we got both of our equations set up. Now what I'm going to do is pretend we forgot calculus. Or let's say we don't know how to do calculus, but we do know how to set this up. Now remember, what we're going to want to do here is we can either solve for x or y in this problem, but I'm going to go ahead and solve for x. Now we're going to take this and plug it in for the y right here. So this s represents sum. You can call it anything you want. Alright, and 3 times, and of course our y is 25 over x, and of course we can actually rewrite this as x plus 75 over x. That's our sum. Now what I'm going to go ahead and do is graph this. Alright, you can see the graph. Okay, so this is 0 on the x-axis and we're coming out to 32 here, and this would be the graph of that sum with respect to x. Now right in here is where we're interested, because this is where the graph, it has a minimum. A minimum is occurring, but we want to find out what is this x value here. That's what we want to find. What is the x value? And let's see, this is 16, so this would be 8, and it looks like maybe just a little bit more than 8 would be our x value. But let's go ahead now and do the calculus. Alright, so the first thing I'm going to do here is I'm going to want to rewrite this, and so we're going to have x plus 75 times x to the negative 1. We want to take the derivative and then solve for x, of course, in this problem. So I'm going to go ahead and take the derivative. Derivative of x is 1. Take this negative 1, bring it out front, and I'll just make that a negative 75. How's that? And x to the negative 2, subtracting 1 from the exponent. Now I'm going to go ahead and just set it equal to 0 and take this x squared down into the denominator, and now we want to go ahead and solve for x squared. And of course, you know, these are the intermediate steps, but I've worked with hundreds, and I guess I could safely say hundreds of students, and this is usually where everybody has problems, and that's just doing the intermediate steps. And you know, once you get the intermediate steps down, I'm here to tell you really that calculus is actually pretty easy, believe it or not. So this is actually a 7 right here. You know, we can actually break this down even more. This is 25 times 3, and you know, these are the intermediate steps. Oh, by the way, remember two positive numbers, so we don't need to mess with the minus sign, right? And square root of 25 is 5, so we can break that down to x is equal to 5 times the square root of 3, which I believe is a little bit more than 8, somewhere in there. You can plug that in your calculator and check it out. Now remember how to get y. We want to come back up here and say y is equal to 25 over 5 square roots of 3, and we can simplify this down. Alright, so 5 goes into 25 5 times, and that's going to be over the square root of 3. Of course, we usually want to rationalize the denominator, so we're going to multiply the denominator times the square root of 3, the numerator times the square root of 3, and this should all simplify down now to square root of 3 times square root of 3 is 3, and we have 5 times the square root of 3 on top. So there you go. So y is equal to, let me just go ahead and rewrite that because that looks like a mess. Actually, you know what? I'm going to go ahead and write my two positive numbers. We'll just write them right here. How's that? So our x was 5 times the square root of 3, right? 5, and of course these are exact values. We don't want to approximate. And then our second number, or our y, is 5 square roots of 3 over 3. So these are our two positive numbers, right? And you can go ahead and plug those in a calculator and get an approximation if you would like. But so anyway, just recapping real quick, we wanted two positive numbers, and we set our variables up. Just let one be x and the other be y. We set up our primary equation. Okay, this is the one we're going to always take the derivative of, set it equal to 0, and solve for x, or solve for y, or solve for whatever the name of your variable is. Then we had our secondary equation here, and we got everything in terms of one variable. That was the whole idea. We solved for either x or y. It doesn't matter which one. You can solve for x in this problem, solve for y. This could be x is equal to 25 over y. It's all going to work out the same in the end. All right. Then we take that, we take our primary equation. We want to get everything in terms of one variable here, and take the, usually, you know, well, in this case we got to rewrite, take the derivative, set it equal to 0, solve for x, and right, once we solve for x, we go back up and solve for y. Now, of course, you know, there's some steps here that I'm actually skipping. In the under this applications of the derivative, when we were doing our first optimization problems, we found what are known as critical numbers. Okay, then remember we drew a graph. We did this, so this was like critical number. We'd put 5 square roots of 3 here, and then we would test, take a test point to the left, a test point to the right, and of course in this particular case the graph should be doing this, since this is a minimum occurring here, and then a plus here and increasing. These were some of the ways that we tested for min and maxes in some previous sections, and if you probably forgot that, you might want to go back and review those things. But I'm kind of skipping this spot, and I'm bringing actually up the graph so we can kind of look at the graph and go from there. But this kind of proves that it's actually a minimum here, and of course, you know, I guess that's important. But anyway, I'm going to assume kind of that you know that already. And basically what we're focusing on are these guys here, and getting everything in terms of one variable and taking the derivative and so forth. All right. Well, let's move on to some more problems. All right, Cal 1, we're doing applications of differentiation. Of course, we're working optimization problems. All right, so we're looking for two positive numbers again, and this time we're looking for the sum of the first, and twice the second is 100. Okay, is equal to 100, and their product is going to be a maximum. So we want to go ahead and set this up. So as you can see, this first part here is going to be the primary equation, and then the second part here will be, I'm sorry, our second part will be the primary equation because the product is a maximum. Well, anyway, let's go ahead and get started. Alright, so we want to let our two variables be, and I'm just going to let them be x and y. Okay, so here's our two positive numbers, right? Two positive numbers are x and y. So let's go ahead and set up the primary equation, and we're going to let P be product, the product of x and y, and remember we're looking for a maximum, so I'll just shorten it to max there. We want this to become a maximum. Alright, and our secondary equation is the it's the sum of the first times I think 2 times the second, if I remember right. Sum of the first twice the second is going to be 100. Alright, so there's our secondary equation. We want to go ahead and solve for either x or y in this problem. Alright, and in this particular case, I think what I'm going to do here is just go ahead and solve for x. So this way you see it done a little differently. Now we're going to take this and substitute it right in for the x up here. So we're going to end up having p is equal to 100 minus 2y. Alright, and then that's multiplied by the y. Okay, so there we go. Now we got everything in terms of one variable on the right hand side, and what we're going to want to do now is take the derivative. But before I actually do that, I'm going to go ahead and distribute this y across. Alright, and now go ahead and take the derivative, so we end up with 100 minus, take the 2 out front, 2 times 2 is 4, y, set it equal to 0, and then solve for y in this problem. So we end up having 4y is equal to 100, and of course y is going to be equal to 25, right? 25 times 4 is 100. So we have found one of our positive numbers, and to find what x is, we're going to go back up into this equation here, and we have 100 minus 2 times 25 is equal to, that will be our x, and this looks like this is going to end up being 50. Alright, so we found our two positive numbers, so hopefully you're keeping up with me here. I know I'm probably kind of working probably pretty fast. Alright, so here's our two positive numbers. Now what I'm going to do here is I'm going to go ahead and go to a graph. Now remember, this is the equation here that we're graphing out. Okay, this is what we want to graph, just in case we forgot our calculus. We want to set up this primary equation all in terms of one variable, right? That's related, of course, to our constraint or secondary. All right, and if we graph this, you'll see that there's a maximum occurring right here. And of course, this is where our y value is located. Well, now hold on. Let's look at this. This axis here is not the y-axis. Okay, the x-axis is really the y-axis. All right, because remember, everything is in terms of y. So let's not get confused on that. But down here, and I've got to go. Actually, you know what? Let me zoom. Man, I've got to really do some zoom. I need to zoom this y-axis. Well, anyway, right in here, you can see, is going to probably end up being right somewhere in here, is y is 25. So pretend this is actually the y-axis here, and this is actually, remember, that's the sum, or the product. I'm sorry, the product. Okay, the x, this axis here represents the product. All right. So there's our 25, and of course, you know, you plugged it in, and we got our x value. So forth. So anyway, I'm going to cut it off there. We're done. We're moving on. Alright, this is Cal 1 Applications of Differentiation. We're working optimization problems. And in this particular problem here, let's read it out. We're going to find the length and the width of a rectangle whose perimeter is 200 meters and has a maximum area. So let's go ahead and translate that into some equations. Alright. So we're looking at a rectangle, and I guess I'll just draw a picture right here so maybe we all know what a rectangle is, even though I'm going to do my best to try to draw a rectangle. Okay, there's our rectangle. Let's say that's our width and that's our length. So we're trying to maximize, we want to find the dimensions that gives us the maximum area, but we've got a constraint here, and that's going to be the perimeter. So remember that the perimeter is going to have to be 200 meters. So let's just go ahead and first write our two unknowns, the length and the width, and 200. So this is just given information here that we're going to need. Now let's go ahead and set up an equation here. Actually, I'm going to write the primary equation first. So we're trying to maximize our area, and I'm going to write just max here, and the area, right? So if you remember from third grade, the area of a rectangle is length times width, And let's go ahead and write the equation out for the perimeter. So remember, the perimeter is this distance all the way around. If we were to measure this all the way around, okay, and we're going to end up having 200 is the perimeter, and that's equal to 2W plus 2L. Okay, so we have our primary equation, we have our secondary equation. Now what we're going to want to do, remember, is get this thing all in terms of one variable, either L or W. And I think what I'll do here is just solve for L in this equation here, or solve for W, solve for L. Anyway, let's just do this. I think the easiest way to do this is multiply the whole thing by a half. Okay, multiply 100 by a half and a half, so we can get rid of these coefficients here, these 2's. So if I multiply this by half, we'd end up with 100 W plus L. Okay, so that makes things a whole lot a lot simpler here. And I'm going to go ahead and actually I'm going to rewrite it like this, so hopefully you can follow me here. Just take the W over to the left, and so, but then I'm rewriting it, flipping it around. Surely you can follow that, right? We got things in terms of W, and now I'm going to go ahead and take this and plug it in directly up here. So rewriting, we're going to have A is equal to 100 minus W, let's put some parentheses around that, times W. So we got our formula up here, and it's in terms of W. Now I'm going to go ahead and distribute that W across, because remember what we got to do next, and that's take the derivative. So 100 times W minus W squared. But you know what, I think before we even do all this stuff, I think what I'm going to do is actually graph this. And remember, we're trying to find a maximum here, and I'm going to graph this, and let's just try to get an approximation first. Alright, so let me bring this graph up, and we need to zoom out on our y-axis, but we're just going to leave it like this. Okay, so as you can see here, let's actually scroll down. Okay, so this is the graph of the perimeter, I'm sorry, the area with, I think we got it with respect to W here. As you can see here, we're at 50 and then 2500. So this X value is what we're looking at. So we should be coming up with 50 in our problem. Alright, so what we're going to want to do is take the derivative of this thing. So I'm going to write A prime is equal to 100, right? The derivative of 100 times W. Alright, so we took the derivative. Now what we're going to want to do is set it equal to 0 and solve for W. So let's do that. Minus 2W, and we solve for W. I'm going to go ahead and take the 2W over here to the left and multiply through by a half, and that's going to give us a W is equal to 50. So remember what the relationship with W and L is L is equal to 100 minus W. 100 minus W. L is equal to 100 minus W. Therefore we can now find L. So we have 100 minus 50, and we get L is equal to 50. Alright, so our dimensions of the rectangle is a 50 by 50 if we're trying to maximize the area. Well, that just gives us a square, doesn't it? Now, we've worked some problems in the past, and it turned out that both of these dimensions are equal to each other. And the quick way to see that is because in our equations there's actually symmetry. Okay, we have some symmetry here, and this is the reason why L is equal to W. It's also the reason why sometimes X is equal to Y, and it's because there is actually symmetry in our equations. Symmetry, and the way I'm saying that is like, for example, this is written, right, just like this term here, 2W, 2L. You won't see symmetry if this was like W plus 3L, right? There won't be any symmetry there. And also this guy up here needs to be symmetric. Well, if we wanted to actually find that area, the area of this square here, we just multiply 50 times 50, and of course that gave us the area. So if you can remember back what the graph looked like, if we can, oh, and by the way, there was a kind of a little error or something. I think I put whose perimeter. I redid this with the find the length and width of a rectangle that has a perimeter of 200 meters and with a maximum area, whatever. I know this is not English class, but I try to do my best on that. Okay, so as you can see here, 50 was our what was that? Our W, and then the 250 is the actual area. So if you forget your calculus, as long as you can set up your equations, you can just graph this stuff and probably get, in this particular case, some exact values. Most of the time it'll be approximation, but alright, well, let's move on and work some more problems. Alright, this is Cal 1, Applications of Differentiation. We're working optimization problems. In this particular problem here, well, let's just read it. I think I actually need to put a period maybe right there. Okay, we got to find the length and width of a rectangle that has a given area of 121 square feet and a minimum perimeter. All right, so let's go ahead and translate that into some equations and see what we can do from there. So we're trying to minimize the perimeter. Alright, so once again we're working with a rectangle, and I'll try to sketch a rectangle out over here the best I can. We'll call this the width, this the length. So our unknowns are L and W, and of course that number that we need to remember was the perimeter was 121 square feet. Okay, we'll just do that, square feet. Alright, I'm going to go ahead and write down, go ahead and write our equations down here. We are, okay, trying to remember what I had going on here. We've got the perimeter, and it's equal to 2W plus 2L. And of course, this is what we were trying to minimize, and I'll just write MIN. I think I was writing it over here to the left. But this is what we're going to try to minimize. This is our primary equation, but P doesn't stand for primary, it stands for perimeter. Right? And we have the area, and the area is length times width is equal to, and I believe I used, 121. Okay. So there it is. We have our two equations set up here, and we want to go ahead and get our primary equation all in terms of one variable. It doesn't matter which one you solve for, L or W, makes no difference. We're going to go ahead and solve for L here, and so we have 121 over W. Now I'm going to go ahead and take this and plug this into the primary equation so we can get everything in terms of one variable, and in this particular case it's going to all be in terms of W. So I'm going to put in our 121 here, W times, what am I doing? Where am I at? I'm up here. Okay. Let me back up. Okay. 2W plus 2L, and this is our L. I'll just put it in parentheses, 121 over W. Go ahead. Let's see, that's going to be 242. Is that right? 242. And I'm going to go ahead and take this W and bring it up into the numerator. Now, of course, what we're going to want to do now is take the derivative, right, and we'll say P prime. We have 2 minus 242 W to the negative 2. We're going to rewrite this again. Right, just taking this back down to the denominator. Now, of course, we take our derivative, set it equal to 0. Set that equal to 0. And now what we're going to want to do is solve for W. Right, we want to solve for W. And I'm going to go ahead and bring the 242 over. We have W squared. And I'm going to go ahead and rewrite this again. 242 is equal to 2 times W squared. Multiplying both sides by a half, we're back down to 121 is equal to W squared, and then we square root 121, and you know, it's always plus or minus here, but of course we're not going to be working. I make these videos in increments of 5 minutes, and so as the first one's uploading, I'm watching it, and sometimes I hear myself make mistakes. In the initial part of this problem here, I need to just go ahead and mention this. I think I said this was the perimeter, right? But the 121 obviously is the area of the rectangle. Sorry about that. Let's get back down to where we were at. So we found W, and of course we're going to be using the positive part of this, and we can break this down a little bit more. The square root of 121, if I remember back from 4th grade, this is 11. Alright, this is 11. 11 squared is 121. Well, we found our W, and now what we're going to need to do is find L. So let's go up here, remind ourselves what that relationship is, and here's the relationship right here. So we have L is equal to 121 over W. L is equal to 121 over, and we said that W was L. And of course that is 11. Right? So we know now what our dimensions are. The width is 11 and the length is 11, and of course this picture is definitely not to scale. Alright, so if the width is 11 and the length is 11, this is going to be a square here. It's going to be a square. And of course I mentioned symmetry in the last problem. By just looking at our equations, we should be able to pretty much tell that both of our values, our length and our width, are going to be the same, are going to be equal. All right. I think that's going to pretty much do it for these rectangle problems. We're going to move on to something else a little bit different. But I'm going to have tons of optimization. These type of optimization problems, application problems, enough to definitely get you to understand how to solve these types of problems. And some of them are going to be pretty darn difficult. But just hang in there. We start with, you know, they all follow the exact same basic format, where we have a primary equation that we're going to take the derivative of, and we have some constraints, or I guess I should say secondary equations, In this particular case, we only have one. Okay, but you know, the real trick is going to be constructing. We're going to have to construct, use a different color here. You know, this is where the difficulty starts to come in, is we're going to have to actually construct these. Okay, we're not going to be given these nice formulas that we've known from the past. We might actually construct our own. So that's going to be the difficulty part, is constructing these things and then moving from there. But you know, once you construct them, like I said, you forget the calculus, you can always plug this stuff into a graphing calculator or something and at least get an approximation. And pretty much in the real world, that's what pretty much goes on. But you know, there was actually, since I've got a little bit of time left, let's get down here to this guy here, and let's actually graph this. Let's make sure our solutions are correct, even though, you know, I know they are. But anyway, we're going to go ahead and just graph this and see what we get for W and even our perimeter, I suppose. So let's just do that. Alright, so anyway, we're just seeing a piece of this graph right here after I'm graphing the perimeter with respect to W. And I don't know if you can see this or not. What is this, 12? Or let's see, increments of, looks like maybe 7 or 8, 8, 16, yeah, okay, so this is 8. Remember, 11 was our W. Okay, so the minimum's occurring here at 11, as you can see, and then of course you could run straight across and see actually what that we're working Cal 1 problems, applications of differentiation, and we're looking at optimization. Alright, so we have a interesting problem here. Now, of course, in the previous video I said we weren't working any more rectangular problems. Well, any more general problems that have to do with rectangles. This is more of a specific case here. The farmer is fencing a rectangular pen for his hogs and needs to find the minimum perimeter with a given area of 10,000 square meters. Yeah, this is a really interesting problem here. There's a lot going on, a lot of hidden stuff going on. Let's see if you can figure it out. Okay, we have some unknowns, and of course, once again, we're going to have the length and the width are two unknowns, and we were given a number, and that was 10,000. This was the area, meters squared, however you want to say this. I think I said SQM, whatever, meters squared. Alright, I guess we are going to draw a picture now, and hopefully you'll understand what we're doing here. I'm going to draw a picture. So this here is some waves, and this is water right here, by the way. This is a shoreline, and out here, well, there's something out here, and I'll tell you what that something is here in just a minute. If I can I think we'll give him a blue eye. We'll do that, and of course we can't figure or forget what that is, right? So let's see if you can put that together and figure out what this actually is. Anyway, I guess I need to get started here. This is a shoreline here, and what's going on is the farmer is going to build a rectangular pen, or at least part of one, and he's going to use the shoreline here as one of his sides. And we'll call this W and this length here. And we're given an area. He said that he needs to have 10,000 meters squared. So the area of this rectangle here is, or part of one anyway, is going to be 10,000 meters squared. He wants to minimize the perimeter. Okay, so we need to find the dimensions of W and L. So let's go ahead and write down our equations. we have, we're going to write down the primary equation first. So that's going to be P, and no, P doesn't stand for pig or pin, it stands for perimeter. And we're going to have two W's, right, a W here and one over here, and then a length, okay, a length. And let's write down a secondary equation. We said that the area is 10,000 meters squared, and this will be W times L here. W times L. All right. Now, this is what actually happened here. He figured all this out and he fenced this thing in. He stuck his hogs in there, and well, he fed his hogs some peanuts one day. And guess what happened? One of the hogs did not like that and he decided to swim off. So we can kind of see part of the hog. Here's his tail and his snout. And well, anyway, he said, I'm out of here, and swam across to the other side where I think he could smell some a little better food than peanuts. He's allergic to peanuts. That pig was. He did not like that pen. Anyway, let's move on to the math problem here. I thought I'd throw that in there. What are we doing? We're solving for one of our variables here. So I always solve for L. It really doesn't matter what you solve for. Solve for whatever you want, I suppose. And of course, I flipped this stuff around and wrote L over here to the left. Now we're going to get our P all in terms of W. So we have 2W plus 10,000 over W. So now we got our primary equation all in terms of one variable. And of course, now what we're going to want to do, I think I left a zero off, didn't I? Whoa. Well, we got our primary equation all in terms of one variable. Now it's time to take the derivative, but of course the first thing we need to do is rewrite this thing so we can take the derivative. Let's not forget some of those zeros. Those could be peanuts, I guess. Alright, let's now take the derivative. So I'm going to say P prime. So the derivative of 2W is 2. Bringing that negative out front. Now we have W raised to the negative 2. And we're going to go ahead and set P equal to 0 and solve for W. And I'm going to write W down here in the denominator. Alright, so bringing this over to the left, alright, let's bring that W squared up towards the top. There's kind of a step that I've been skipping on these optimization problems, and I'm hoping that that you work some of the previous stuff when we started initially finding mins and maxes and so forth. Right, so we multiplied a half times both sides here, and that was doing a number line and testing, testing our critical numbers. If you had a critical number here, testing to the left and to the right, and seeing if your graph, increased, decreased, and all that. Well, I'm leaving that part off and hoping that you guys, know how to do that. I just want to kind of focus on the process of these application problems. Well, I guess that's application problem there too, but more, I don't know, specific, more real world kind of stuff maybe. Alright, we got to take the square root of 5,000, and hopefully you know how to do that, but I'm going to go ahead and break this down. This is ends up becoming 50 times the square root of 2 is going to be our width. And just for the heck of it, I'm going to do a little approximation here. This actually approximates to 70. I'll just round it to one decimal place, 70.7, and of course this is going to be meters. Okay. Well, we found our W. Now what we're going to need to do is go back, find that relationship between W and L, and find what L is. And L was equal to 10,000 over W. So let's actually try to remember that, right? So L is equal to 10,000 over W, and W is going to be 50 times the square root of 2. Okay, and we can break this down and simplify this, because 50 goes into 10,000 and so forth, but I'm just going to leave it like that. The whole idea here is to find out what L and what W, right, what those values are. But so we found L and W, and if you would like, you can always get those numbers and take them and plug them in to actually find what is this actual parameter. And of course, I always suggest that you graph this and take a look at those numbers. And of course, the what you want to graph is that guy right there, right? All right. Well, I'm going to leave this secretive problem to you to figure out why the hog left the pig pen, because we were throwing peanuts at him, right? All right, we're going to move on now to another problem that's probably going to be similar to this.